So I'm delighted to introduce Professor Hobbs from Cranfield University, who's here just for this afternoon to talk to us about some novel radar collection methods.
Right. Okay.
Yeah.
Right. Thank you very much. Well, thank you very much for the invitation to come and speak. We're always happy to talk about geosynchronous radar and try and sort of grow the community who know about it and are excited about its possibilities. My background is that I've worked at Cranfield actually since graduating from Cambridge. I went to do a 3-year PhD, and 42 years later, I do have my PhD. I've worked in, sorry? Yes. I've worked a whole variety of things, generally measurement systems. So my background is physics. That's what I did as an undergraduate. Actually did in those days, I don't know if you still do it, I did the maths tripos in my first year, and then 2 years of natural sciences, which is all, for me, was all physics and maths. Then went over to Cranfield, did the PhD, got interested in radar. We started using radar for insect migration, and then from radar into space. And I've been running the space group now at Cranfield for the last 10 or 15 years. So my background really through working at Cranfield has been very much on the sort of engineering side. So rather than fundamental theory, we tend to do a lot of work much more applied. So I think what you'll see coming across in my talk is, well, system engineering is what we like to think of ourselves as, so that on some of these projects, I've been worrying about everything from the science case for sort of why glaciers are melting in the Alps, and therefore what measurements you need to make, what the payload's got to be designed to do, what the satellite orbits have got to be, really thinking, trying to put the whole system together is the area that I've been working on. So hopefully I'll be able to flag up a few areas where we need, well, I think you'll see the sort of complexity of the signals that we're dealing with. It's not that it's necessarily a complicated radar as such, but there's so much going on that we need to tease apart to try to get to the geophysics, which is what we're really interested in. So what I'm going to talk about is really the why and the how of radar imaging from geosynchronous orbit. Why back to first principles? Well, because geosynchronous radar brings in a number of features which make it pretty much unlike other sorts of radar that people do, because of the orbit that we're in, the long integration times that we've got, and so on. So I think it's useful to go back to some of those first principles just to remind ourselves of where we are, what's driving the mission design the way that it is. Looking at some of the challenges, so that really leads on really from that, things that are sort of particular about doing radar imaging from geosynchronous orbit, and then potential and prospects. So potential is really built on the science case for this mission here. So I led the study for the European Space Agency. We completed this in December 2020. We had a fair amount of ESA funding for the science team. There are 2 industry teams working in parallel, and this is the fruit of our work, really looking at the potential for a geosynchronous radar mission. It's one of the concepts that the European Space Agency is considering for a future Earth observation mission. There's another opportunity come up at the moment, Earth Explorer 12, and the team is back together again. We're keen to see this happen. So we're putting together an updated proposal. If that were to go ahead, then it would be the mid-2030s when this mission were to fly. So I'll be well retired by then, but hopefully coming back to some of these sort of workshops and so on to find out these exciting new results this mission is delivering. So a couple of slides really just on, when we talk about geosynchronous radar, what actually is going on here? What are we really thinking about? So let me just organize the screen there. Yeah. So geosynchronous orbits, this is the orbit that Arthur C. Clarke got as 1945 when he published his article in Radio Science about there is this orbit out there where the period is exactly the same as the Earth's rotation on its axis, and therefore you put a satellite there, it's basically on a huge tower with a permanent view of the Earth disk in front of it. That would be really exciting actually for a radar to monitor what's going on Earth's surface, because you could do whatever temporal sampling you wanted. So out at geosynchronous orbit, you're out at, I think it's 6.6 Earth radii out. if you're in low Earth orbit, where nearly all the other radar, well, in fact, all the other radar satellites are, you're only about 0.1 of an Earth radii out. You're really skimming the Earth's surface. Those orbits just go around like clockwork. You haven't really got any control as to where you're passing over. You just have to do with whatever the orbit takes you to, because it's so expensive in fuel to change from one low Earth orbit to one that's significantly different. So those orbits in those low Earth orbits just go around like clockwork, and they have to wait for the Earth to turn underneath them enough times for the orbit track to repeat itself. So for example, the current Sentinel-1 missions, they've got a swath that's about 250 kilometers wide, and an individual satellite repeats every 12 days. That sort of 12 times 250, about 3,000 kilometers, that's the distance between orbit passes. So in terms of one low Earth orbit, the Earth has turned about 3,000 kilometers at the equator. So that sort of constrains what these low Earth orbit satellites, how they can do their image repeats. So if you wanted frequent imaging from low Earth orbit, you've got to have lots of satellites. So there are some low-cost satellite constellations coming up now. So maybe that's one route to do the fast sampling that we want to do. But another one certainly is to sit out at GEO and just to image as and when you want. The sort of mission we're thinking about in Europe is one with an antenna area of about 50 square meters. So what's that, sort of 7 to 10 meter diameter? Only a few hundred watts of RF power being sent out from that. And typically we're looking at C-band, so wavelength around sort of 5 centimeters. That, as much as anything, gives continuity with lots of previous missions that we've operated in Europe. So going back to about 1990 when ERS-1 was launched, since then ERS-2, ENVISAT, and now the Sentinels, they've all been C-band emissions. So there's a good body of understanding as to C-band backscatter. Plus, it's quite a decent compromise. If you go to longer wavelengths, you have to worry more about the ionosphere, and you have to worry more about getting very big antennas. If you go to shorter wavelengths, then the sort of water vapor in the troposphere more easily corrupts the signals that you've got. And also you're seeing things like the surface of vegetation canopies rather than being able to penetrate into it and see the soil. But some of the great things about it are this really unprecedented temporal sampling. And if you're sitting out at GEO, you could image Africa, Europe, whenever it suits you, pretty much. There are some constraints depending on the details of the orbit, but largely you've really got just unprecedented freedom in terms of your temporal sampling. Also, what's quite nice about it is it's from the radar phase. Basically, we're able to measure the atmosphere and sub-centimeter ground motion. From the backscatter, we get things like sort of maybe soil moisture, but the normal sort of radar imaging. And also sitting out there, if there were to be, an earthquake, landslide, flooding, you could almost, within minutes, you could have switched your radar to start to image that area. So your response in terms of emergencies is really, so much faster than we can do with current low Earth orbit satellites. So there's plenty of interest there. Oh yes, the orbit that we're in, I've said geosynchronous. Some of you may know that if you just park a satellite out there and then switch off the orbit control, it eventually, the inclination starts to rise, and you end up with an orbit that's doing a sort of elongated figure of 8. If you do control the orbit, though, you don't have to stick with that. What's interesting to us is generally to have some sort of east-west motion in the orbit. So you can get that just by making the orbit slightly eccentric. Then that gives you east-west motion. If you wanted, and that means that if you're sitting over the equator, you can image to the north or the south quite nicely. You've got resolution in 2 image coordinates then. There's a couple of slides now coming up on, sorry.
Just to cover, the aspect formation gives you the SAR.
That's right, yes. So, yes, so I think that's coming up.
Not everyone's very nice.
Ah, right, okay, yes. So I wasn't quite sure who I was speaking to really, but right, okay. Well, some people will find this hopefully very familiar ground. Others of you might find it a little bit more novel. With radar, you're able to measure range from just timing. You send out a pulse of radar energy and time, basically how long it takes for that pulse to come back to you. and that tells you your range resolution. If you send a very narrow pulse, then that gives you good range resolution, and a narrow pulse corresponds to having a big bandwidth. So typically, if you had a bandwidth of 1 megahertz or equivalently a pulse of 1 microsecond, that gives you a range resolution of 150 meters or 10 megahertz. Divide that down by a factor of 10.
What do you mean by range here? I guess the scene is actually at right angles to the radiation.
Yes, so that radars.
What does range mean now?
Radars, we're always side looking. So range gives us, so as conventionally with satellites, the satellite's moving along and then range is out.
Yeah, so you're now geosynchronous, so you're now looking straight at the equator, right? So you can't image on the equator.
That's right, yes. If we go down to the equator, because we're sitting right over the equator, everything's at the same range. Yeah. So it's not very interesting. Okay. There are some radar altimeters that use that, you know, radar altimeters, they're just measuring the height, but we're not so interested.
So on your previous slide, when you said 20 to 60,
yes,
which is the zenith.
Yes, so that 20 to 60 degree angle, that's the angle away from the vertical, from the zenith. Yes, so if you go less than 20 degrees away from the zenith, then you get closer and closer to that sort of specular backscatter.
So a bit just from just below the tropics up to.
Yes, that's right. Yeah, and in a circle around the subsatellite point. It is a sort of area that we can read. So range gives you one image coordinate. We need another another 1 or 2 image coordinates as well to help us out. The way that we get what we call azimuth or a long track resolution is by this aperture synthesis technique. So the diagram here shows you, well, this is the diagram I use for the normal sort of lectures to our MSc students. So what you've got here is a satellite moving in this picture from position A to B. The thing that's special about positions A and B is A is the first point at which the beam illuminates this target area here. B is the last point at which it illuminates this. So these lines here show you the limits of the sort of beam width.
Sorry, I thought geostationary.
Yes.
So it's the one.
No, I tried to use the word geosynchronous, not geostationary. Even so, it is moving.
Okay. Yeah, right. So it's the point below it on the Earth.
Yes. It moves so that if you give the orbit a little bit of eccentricity, yeah, then you're moving in and out in range, but that also correlates with east-west motion. So we can control the eccentricity to give us the east-west motion that we want.
So the point underneath the satellite on the Earth.
Yes, that doesn't move backwards and forwards, yes.
Because the satellite speeding up and slowing down on the eccentricity.
Very, very slightly, yes. Yeah, so you know, the eccentricities, I think, are, you know, 1 part in 1,000 away from 0. Yeah. Okay, so satellites moving from A to B, it fires the radar multiple times. So all those blobs are the radar firing a pulse. Typically, in low Earth orbit radars, I think there's about 1,000 blobs from A to B, as it were. So we've got 1,000 pulses worth of information. And all of those pulses, they've got everything in this beam, but all of them have got some information about this target backscatter. So then what we can do in signal processing is we'll recreate an aperture that goes all the way from A to B, in this case here. One of for once, nature's kind to us. And it turns out that the resolution that you can achieve from that, if you integrate all those signals, is that in this standard imaging mode where you're doing what we call strip map imaging, you're moving in one direction, you're imaging off to the side and just sweeping your beam across as your orbit goes forward. In that strip map mode, the resolution you get out of this is actually, it just falls out, is actually half the real size of the aperture. Now, the wavelength cancels out, the height of the orbit cancels out.
That's the antenna width.
Yes, that's right. Yes, so that on the ERS, well, actually on the Sentinel-1 satellites currently flying, the antenna is about 10 meters long. They get a nominal resolution of 4.5 meters out of that.
Right.
So, you know, it really does work.
There's the real aperture and there's a synthetic aperture.
Yes.
And the resolution is the function of the real aperture.
Yeah, purely. Nature isn't usually that kind to us. And so that in low Earth orbit, this synthesized aperture from A to B could be of the order of a few kilometers. The important thing here is that we're going to use this synthetic aperture mode. In geosynchronous orbit, we might only be moving, the whole orbit length might only be, say, 140 kilometers, whereas our footprint is 400 kilometers. So actually in geosynchronous radar, we don't actually get as far as being able to fill the whole, as it were, sort of explore the whole aperture typically. But that doesn't matter too much for some of the modes that we're interested in. So basically we're in what radar engineers would call spotlight mode. So we just keep staring at the same spot on the ground as the satellite moves around in its orbit. So if you're out in geo, sort of, you can be permanently collecting data from a region, say around the south of the UK or Morocco, you know, patches of a few hundred kilometers over Morocco.
What kind of temperature length are you thinking about?
Typically kilometers, but we're traveling at meters per second. So that means minutes of integration time.
And this is quite far away. So the angle swept.
Yeah, 40,000 kilometers away, roughly.
Probably geosynchronous wouldn't give us that. Beyond two, probably because beam width so large.
The beam width is, well, with that sort of 50 square meter aperture and, you know, 7 or 10 meters, you're getting footprints on the ground. Well, I think we've got the sums here. They're several hundred kilometers in size.
So that point on the ground won't feel the extent of the real aperture.
No. We typically wouldn't do that, but because it would take so long to do it, really, it would occupy the whole of the day to practically to explore that aperture. Some space engineering here is that the way that we divide up this geo ring for communication satellites is to give them slots which are a nominal longitude position plus or minus 0.1 of a degree. In kilometers, that's plus or minus 73.6 kilometers. So when I said 140 kilometers, I'm thinking of going the sort of the full extent of one of those standard single geo slots. As far as I'm aware, it's a little bit hazy as to what actually we would really be allowed to do. From the previous study we did with the European Space Agency, they seemed to be assuming that actually we could have a whole 1 degree slot, which is something like 700 kilometers across. That means we can make bigger synthetic apertures, or we can make a given size of synthetic aperture much more quickly because our relative orbit speed is higher.
You have to go on that with your neighbors.
Yeah, yes. So, well, I think to quote, is it the Hitchhiker's Guide to Galaxy? Space is big. Right. Yeah. Yeah, but one of my other hats, we worry about sustainability of space, and space debris is actually a serious problem.
Especially in this.
It's fairly congested. It's very valuable. That geosynchronous ring is really quite valuable orbit space. So we don't want to do anything to create accidents, collisions in that orbit space.
So presumably the east-west motion is so you can image the northern.
That's right. Yes. Yeah. So if you're sitting over the equator, say at around 0 degrees plus or minus 10 degrees, or there's the Atlantic out to one side. With our technique, because it takes so long to integrate, we can't really usefully image over ocean surfaces.
There's no restriction on the side of the ground.
No.
Not south.
Yes. So that the Chinese have got some geosynchronous radar mission concepts, which are supposed to be pretty much ready for launch, I think. They're working on, they're a little bit cagey about exactly what they're doing, but I think it's an L-band one, so longer wavelength, very big aperture, sort of 25 meter diameter. And I think they're going to put it into something like a 15-degree inclination orbit. They've done studies where they go up to 50 or 60 degrees inclination. But to make those work, you need very big apertures, like sort of 50-meter diameter, and very high power.
1 day per aperture.
Sorry?
1 day per aperture.
Yes, you've got a huge aperture there that you could create, thousands of kilometers.
Yeah.
So they can get a nice spatial resolution, but to make it all add up, they need very large signal. They need very large apertures to collect enough power to make a decent signal, and high power transmitters, both of which are very expensive, stroke challenging technologically. So in our case, in Europe, I suppose we've tended to be quite pragmatic, knowing that the European Space Agency just isn't going to pay for one of those really high inclination orbit missions with very high power transmitters. So we've tailored our ambitions to these lower speed orbits where we're traveling of the orders of meters per second. So you can see with that one full slot, plus or minus 73 kilometers, that gives you a relative orbit speed at peak of just over 5 meters per second. And it's very sinusoidally, so that's in the middle of the orbit. As you get towards the tails, it drops down to 0, and then 12 hours later, it'll be back to 5 meters per second going the other way. In our case, because we're not doing this strip map mode, our synthetic aperture is really made by that speed, at whatever time of day we happen to be doing our image. That's the speed multiplied by the integration time. So if you've got, say, 5 meters per second multiplied by a minute, so at the bottom here, for an integration time of 1 minute, you get a synthetic aperture of just over 300 meters. You do the sums there for working out what your azimuth resolution is. So this is like the long track resolution. But altogether, it comes out as 3.6 kilometers. So to use these sort of missions, you've got to find applications where you don't need really fine spatial resolution. We can go down perhaps to sort of 100 meters. In this case, it takes 36 minutes, looking at 1 kilometer in 3.6 minutes of integration time. But that starts to work with these sorts of numbers. If we could have the full 1 degree slot, then we can bring these numbers down by a factor of 5 because the satellite's traveling that much faster. But to do that, you need to have a bit more transmit power to get the signal to noise ratios to work, or a bigger aperture. And both of those are expensive.
These all have the same noise signal 0.
Sorry?
These all have the same noise signal 0.
I'll pass on that question, but you're integrating for.
When you literally integrate for that.
Yes. I have a feeling that the image quality comes out the same in terms of the azimuth resolution, because as you go integrate for longer, you're going for finer spatial resolution, so that what you gain on one, you lose exactly on the other. But it is a bit of a game to juggle. There's so many parameters with this to juggle in terms of how you're integrating your signals, the integration time you choose, and so on. That designing it is quite an art. We've had several years of discussions of this really with these ESA study, both industry teams and the science teams, getting our heads around exactly how to make the system work best. And I think there's a question about, is this a system for getting interferometric data, in which case you might design it in one way, or for backscatter data. We tend to think the interferometric data is probably more valuable to us, in fact, but really because it's more amenable to averaging and therefore retrieving signal from the appropriate averaging. Okay, so hopefully these have given you a bit of a background for the numbers that we're involved with for geosynchronous radar. I'll take my watch off, just keep an eye on the time. So, why do we need to go back to sort of radar basics? Well, with georadar, it's not really like low Earth orbit radar where these orbits go around at a steady speed, you're always looking more or less perpendicular to the velocity. Instead, we've got so-called squint imaging, depending on our velocity might be mainly east-west, but we can be looking in almost any direction relative to that. We're not limited to looking perpendicular to the velocity vector locally. Typically, over these integration times, we need to take account of the curvature of the orbit path as well. So it's much more like airborne radar than conventional low Earth orbit radar. So the engineers at the European Space Agency were very familiar with low Earth orbit radar. We're having to start again from square one in terms of thinking through their basic radar principles to get a grip as to how to make georadar work. And the thing about the long integration time is that, well, so much is changing. The atmosphere and the surface are both changing in those times, and that causes us various challenges, but it also makes the atmosphere in particular measurable. And we're looking at some of the surface changes as well, whether there are changes in sort of plant physiology that we can pick up through these sorts of missions that open up new science. So instead of just looking at, as with the current Sentinel missions, you only ever see the land surface at 6 a.m. or 6 p.m. We can see it at, right through the diurnal cycle, and maybe we'll see things happening to vegetation that just isn't apparent to conventional missions. Some of the things that worry me are some of these image features due to sort of azimuth displacement and blurring. I've got some numbers here just to work out. I just did it sort of for my own fun, really, just to see what these numbers are really like. But assuming we've got that 200 watts out in geo, a 50 square meter antenna, and we were trying to image something with a spatial resolution of about 100 meters on the ground, and the backscatter coefficient of -10 dB. So effectively, a tenth of the power is being scattered isotropically. You follow through the numbers, and you get that, well, 2 microwatts is being scattered from my 100 meter square patch of ground. That is being scattered isotropically. So what I collect back out at space in my satellite, even with a 50 square meter antenna, is down to what's it, 5 times 10 to the power -21 watts. So not a lot of power for my signal. But look at the noise that I've got, or the sort of bandwidth I might have would be about, say, 10 megahertz. I end up with a noise power, which is about 10 to the -13 watts. So I'm starting out with a signal to noise ratio of 10 to the -8. So radar engineers really do believe in statistics. It's statistics that make our missions work. It was a bit shocking when I first saw that number, but we've got a few tricks up our sleeve, which we routinely use for these sorts of situations. And in particular, we can do pulse compression. So instead of sending out just all our image energy in that, say, 100 nanoseconds, we can actually stretch the pulse over a much longer period of time, code it. So typically we ramp up its frequency. And then in the receiver, you have a sort of a matched receiver, I think it is, which sort of compresses that bandwidth all down into an equivalent very narrow pulse. So that pulse compression gain, that gives us something like a factor of 1,000, 10,000, so another 30 or 40 decibels. And then coherence integration gain, we integrate many, many pulses. And again, we can use that to recover signal to noise. And by the time you've done your integration for tens of seconds or maybe hundreds of seconds, we've recovered, 80 plus decibels to give us a decent usable signal to noise ratio. Clearly, if we go to finer spatial resolution or to surfaces with lower backscatter, then life gets more difficult. If you've got radio frequency interference, again, life gets more difficult. But we're starting to get to numbers where we can make things work. In general, because of the difficulty of going to fine spatial resolution, 50 to 100 meters is about as fine as I think it's sensible to go out at geo. If you want to go finer than that, really, geo isn't the place to be to get fine spatial resolution. In terms of the atmosphere, well, what can we do about it? We've got the ionosphere and the troposphere to worry about. The ionosphere, a bit like GPS, you've got enough bandwidth within the sort of regulations, so that at C-band, we've got something like, I think, 120 megahertz available. you can use, so as it were, both ends of that part of the spectrum to make real-time measurements of the ionosphere. So there are techniques for, in real time, correcting for the ionosphere. But if you don't do that, then you're just going to have to live with perturbations due to the ionosphere. The troposphere, we can't play any games like using that bandwidth to resolve the troposphere. We've got of the order of, well, sort of 2 or 3 meters nadir path on a slant path, quite a bit more delay than that, which is going to affect our images. But if we can find ways of correcting for these, we're in real time making measurements of the atmosphere, both ionosphere and troposphere, over scales of hundreds of kilometers, with good temporal resolution. So meteorologists, atmospheric scientists interested in the ionosphere, this potentially is quite a powerful source of data for them. I'd have done some work trying to analyze these. So this plot here, I don't know how well the colors are showing up, but what I'm trying on this plot to capture is various length and time scales, so that the dark colors up top right corner are trying to represent typical length and time scales, say the ionospheric perturbations and the tropospheric perturbations. The ionosphere particularly affects the long wavelengths. The troposphere actually has more effect on the shorter wavelengths because, a centimeter's delay, if you've got a 40 centimeter wavelength, isn't such a big deal. If you've got a 2 centimeter wavelength, then a centimeter delay is quite a lot of phase that you've got to worry about. So the troposphere causes problems at short wavelengths, the ionosphere at long wavelengths. What I've done here in the lighter colored shading is to show regions where fluctuations in the ionosphere and troposphere would actually decorrelate the signal, would mean that you are no longer coherent over your integration time. So the images in the clear part of this figure are that's regions where you can do imaging, and then these diagonal lines here are representing different wavelengths. So at the top, with a frequency of 0.75 gigahertz, that's a 40 centimeter wavelength. The dotted line is 20 centimeters, dashed, 5 centimeters, and so on, down to 24 gigahertz, where it's just 12.5 millimeters. So these are representing different wavelengths. C-band's sort of somewhere in the middle there. Basically, what we can do, though, is if you measure in the clear part of this, so with short integration times, relatively coarse resolution, you redraw these sort of plots for different orbit speeds. So this is drawn for quite a low orbit speed of 1.8 meters per second. If you're going faster, you get a bit more resolution out of a given integration time. But basically, if you can make your measurements in the clear part of this, and then make a time sequence of those measurements and process them appropriately, you can actually work out what the atmosphere is doing. As long as the atmosphere isn't doing things on finer spatial scales than you're measuring, you ought to be able to deduce what changes there have been over that period of time in the atmosphere. Once you know the atmosphere, you can then correct for it. So then you can move right on this diagram, go to longer integration times, having corrected for the atmosphere, and then you can get your fine spatial resolution. But clearly there's quite a bit of signal processing to be done there. And I think it's one of these situations where we need the atmosphere to be kind to us. Some severe weather systems, very turbulent, big contrast in refractive index over short time scales, we just probably would have to hold up our hands and give up on those. But that really intense weather hopefully would be quite rare. And even so, we could probably put delimit it and say, in this region, there was very severe weather going on over a short time scale. We don't know exactly what's happening, but it was certainly severe. So that's the atmosphere. For the surface, I don't know how much you're familiar with radar, but those of us in the radar world were very impressed when this came out. Got on the front cover of Nature, actually showing you using a pair of radar images which were coherent with each other. Therefore, you could use the phase information. The phase difference allows us to map out the distortion of the Earth's surface around the line of an earthquake. So if you've got sort of coherent motion of the surface, coherent over a group of pixels, and you've got a nice, clear sort of phase, nice and stable from that, then you can actually measure displacements of the Earth's surface down at sort of sub-centimetre scales. So geophysicists really now routinely make extensive use of this. Some reasons on this will be just basically phase noise, so particularly close to here, or if there were areas of woodland or open water, then the phase just isn't stable from one image acquisition to another, and it's just random in those periods. So we get those sorts of problems with geosynchronous radar. But one of the other features, which is a bit of a challenge for us, I think, is the sensitivity to radial motion. So it's well known in synthetic aperture radar that if you've got a target that's moving, and particularly moving radially towards or away from the radar, then you get sort of imaging ambiguities. So that the picture there shows you, well, it's a sea surface with a ship on it. What you can actually see is the wake of the ship in the dark line sort of horizontally across the middle of the image. And you can just about see that the bow waves from that, making sort of triangular shape. And then the bright blob displaced from the tip of that bow wave pattern is actually the ship. And the reason is well understood. A moving target causes image artifacts, which mean that they appear to be displaced. Now the ship is all moving together, so it's all displaced down to one position, offset from its true position. If you've got something like forestry, so branches and leaves moving around, some of the backscatter power will be displaced one way by a large amount, or the other way by a short amount, depending on the sort of random motion of that vegetation canopy. And it basically sort of spreads out the backscatter that should be coming from that part of the image where the forest is over a broader azimuth area. It also turns out that changes in the atmosphere between the radar and the target can have a similar effect in that they change the phase path between the transmitter and the target. So if you had, say, a warm front bringing moist air across the scene over a period of a few minutes, then in principle, that could cause you these sorts of azimuth changes. That might come, and it's saying on a day like today, if you've got a very humid, warm air going up under cumulus cloud, and that was advecting across the landscape, then you'd also get this sort of azimuth displacement due to that.
That would happen with the whole scene, and the bow waves would also be displaced, as well as the boat.
Yes, well, I've got some images coming up where you can see it sort of shimmering in the whole image. Okay. I set up a simulation where I basically had a sinusoidal refractive index pattern advecting across a landscape, and you can see the ground targets just shimmering in there.
Characteristic scale,
well, the sort of thing that worries me is they see those azimuth sensitivities in low Earth orbit. Oh, I don't know if I need to play. I'll try and explain this diagram here, but it's when people talk about these azimuth shifts, they usually go into Doppler concepts. I don't really like Doppler. Somehow it seems to hide the physics from me. So the way that I think about this is that, again, I've got things at position A and B. So I'm thinking I target at position A, and then that V nominal is the true satellite velocity. If my target A is moving towards the satellite, then in an imaging situation of my target, it's the same as if the satellite swung slightly towards my target to give the same velocity component down towards the ground, but the target stayed stationary. If all I'm thinking about is imaging target at position A, either I can think of it as the target moving towards the satellite or the satellite moving towards the target. If I think about it as a satellite now moving towards the target, the satellite's velocity is swung round by a small angle, and then the moving target at position A has the same phase history as a static target at position B. So actually, because my image processing assumes everything's static, it's put my target at position B rather than position A because of its motion. And if you work out the geometry, that comes out that the azimuth displacement, well, that angle is just the ratio of velocities, multiply that angle by the slant range, and that gives you the azimuth displacement. So no need for Doppler parlance at all. We've got our answer out, just from basic geometry. But if you look at the scalings, in low Earth orbit, that azimuth displacement is 100 meters per meter per second of radial velocity. The geosynchronous radar, because we're so much further away and we're going so much more slowly, the displacement, well, it's 10,000 kilometers per meter per second, or 10 meters per micron per second. So there's all sorts of things that are moving at speeds of microns per second or faster. We were working it out earlier today. You know, Earth tides, solid Earth tides, say 20 centimeter displacement over 12-hour period, so plus or minus 10 centimeters. That I think came out as a 14 microns per second. So 140 meters will be the displacement. So we would expect, you know, if we can resolve images down to 50 meters, we should see that azimuth displacement due to Earth tides. So things we've never had to worry about before with low Earth orbit radar suddenly start to become things, well, maybe we could measure it, or maybe we've got to worry about it, because unless we compensate for it, it's going to screw up some of our imaging. And in terms of if anything worries me about the signal processing, it's really that exquisite phase sensitivity. You know, orbit drift, clock drift, there's all sorts of things that could cause me those sorts of problems. Here I've got I tried to embed a video into the presentation, but I couldn't get it to work. What I've got is just 4 stills from a video of a simulation where I've simulated a regular grid of points on the Earth's surface. So they were just in a regular rectangular grid. And then I've advected a sinusoidal phase screen, so with the refractive index of the atmosphere changing, and then let that advect like it might be carried by the wind across the landscape. And really what you can see is that what ought to be a regular grid of points is distorted because of this effect of the refractive index above the targets changing. I suppose it's a bit like if you're looking through a stream and there's ripples on the stream, and you can see the pebbles at the floor of the stream sort of moving around a little bit as the wave pattern goes over. But, you know, all sorts of things. We're going to show Earth tides. If you've got, say, buildings or, you know, large structures built of steel that warm up during the morning, maybe as they expand, if they've got speeds of the order of microns per second, that could be a measurable displacement that we would get with georadar. So I expect all sorts of image artifacts to show up if you were to get one of these georadars working. Partly that's an annoyance, but maybe that's information actually, if you understand enough about it, to tell you about what your targets are doing. But it's certainly new ways of thinking about the imaging. All right, so that's 45 minutes there on radar, principles of georadar. Now I've got 20 slides or so to tell you about some of the science that we might do. But a lot of it is focused on sort of hydrometeorology, weather systems. It's really aspects of the water cycle where significant things are happening within a day, or maybe over sort of minutes or hours. So in our science team, we've had people who are experts in some of these very intense storms you get around the Mediterranean, particularly sort of summer into autumn. They can be really intense, cause very severe localized flooding. And, you know, there are statistics of, well, I feel a bit awkward, really. As scientists, part of the motivation for our research is, you know, saying how important it is. As part of the importance here is that, you know, there are some of these events caused where people's lives have been lost because of flooding or of earthquakes. So that some of these natural disasters, I don't really want to gloss over those losses, because, you know, to the people involved, those are serious losses. But for us, maybe that's a motivation for, if we could improve our weather forecasting, we could provide better protection really for those people. And a georadar might potentially provide that. The water cycle clearly is pretty much fundamental to human society and to the environment. So clearly it has importance. The sort of motivations really as well, I think are, well, climate change. We're expecting changes in the dynamics of the water cycle. We need improved understanding in a number of aspects which we don't yet have. Advances in modelling, as we're going to finer and finer spatial resolution, then having measurement techniques such as a geosar that could tell you what the atmosphere is doing on commensurate length and time scales might actually have real value. And clearly global change, a lot of these societal issues around the water cycle really puts more and more pressure on us understanding and hopefully being able to manage these things better. In terms of the science goals, these are really some of the things we've been focusing on. So mesoscale convective systems, whether they're around the Mediterranean or say in the Sahel. But generally, it turns out that these mesoscale convective systems in the tropics can be responsible for half of the annual rainfall. And the predictions are that with climate change, that'll get more important. And it turns out that they're not as well understood as we'd like. So that there are, there's mismatches between predictions and modelling at the moment. The surface water budget, really just understanding, if there is rainfall, how's that partitioned between the vegetation, canopy, the soil, runoff? Well, measurements that actually allow us to see how the surface moisture is changing over timescales of, say, every hour or so could actually help us observe that. That's what these sort of cartoon on the right is about, really, trying to sort of pick out how soil moisture and surface, the vegetation water, you might actually be able to see changes in surface backscatter at the same time as you're seeing the refractive index of the atmosphere change as moisture goes from the surface back into the atmosphere. And then because we're making these very sensitive phase measurements, that tells us also about motion, such as glacier motion, as well as, say, snow accumulation from the phase measurements. And then the other area is the solid earth. So it's not really directly water cycle, but because we can see these changes in the Earth's surface, like that nature front cover picture, landslides, volcanoes, earthquakes, we can make useful observations really at fine timescale for the first time of these sorts of phenomena. We liked this picture here. We don't need to go down the detail too much, but what it's really showing is that of all the space-based measurements, water vapor from GNSS, so basically from satellite measurement systems like GPS, GLONASS, and so on, those water vapor measurements are one of the most powerful measurements for a meteorologist. So we were hopeful that a mission like HydroTerra, which actually can operationally make measurements of water vapor mapped over hundreds of kilometers regionally, that could actually be a significant input for meteorologists. So this is some of the work on the storms around the Mediterranean. They simulated some of the measurements. This is the one. Yeah. So on this slide here, what we've got is actually it is a live animation, so this one's working. What it's comparing is on the far left is the sort of observations we think we could get from HydroTerra or a georadar. So basically water vapor over the land surface as well as backscatter. In the second one, you've got an hourly rainfall map from numerical weather prediction. So really just showing you the sort of inputs to the system. On the third one, you've got the low Earth orbit radar. So occasionally you get a flash of color. So every few days, basically Sentinel is going to give you a strip like that, but for most of the time you get nothing. And the Sentinel is only at 6 a.m. or 6 p.m. And then on the right, we've got what you can get from GPS. So really, we believe there's huge value potentially from a georadar mission that could help you to monitor the atmosphere pretty much continuously. And if I can go back. Yeah, so taking those sort of HydroTerra-like inputs into numerical weather prediction really helps pin down some of the positions of these intense rainfall events. And therefore, you've got a much better handle on the flooding risk of particular locations in a way we can't currently do very comfortably. This is another aspect of the mesoscale convective systems. So in this case, over the Sahel. And basically, there's a mismatch between the predictions at the moment and the observations. So I think the predictions are showing, sorry, I need to, this diagram on each of those plots is what you need to be looking at. In the models, we've got sort of rainfall in the morning. The observations are that you get rainfall in the afternoon. So something's not right there. And so improved observations of actually how these mesoscale convector systems operate over regions like the Sahel could give you a much better handle on that. And as I said, these convective systems, they're responsible already for half of the annual rainfall, likely to get more than that as we go into the future. So, you know, a significant climate-related inputs there in terms of understanding the water cycle. You've seen that slide there. This one's looking at the sort of surface water budget. It's really tied up intimately with the surface energy budget, because energy, it either warms the surface or drives evaporation. So getting a better understanding of how the sort of surface moisture is partitioned between, say, soil, vegetation, and the atmosphere is something that we think we can make a useful contribution to. This is from a set of simulations that were done by the French Met Office, so CNRM. And what they were doing is looking at, again, sort of on the left, inputs from precipitation. In the middle, they've got a model for how much moisture is held on vegetation. So, you know, sort of raindrops sitting on the leaves of vegetation. And then on the right is what moisture is in the soils. And from their simulations, they're showing different timescales for these different processes. We think we can probably tease those apart using frequent observations, such as you might get from a geosynchronous radar. So again, sort of linking into the water cycle, this surface energy balance, better observations really for the first time to allow us to tease apart all these different processes. Really built on the work that we did for Hydroterra, ESA's invested in a number of field campaigns. So hydrosoil is one of these. We're about to start a sort of next generation of hydrosoil. And in this case, it's down at Barcelona, where they happen to have one of the university buildings just alongside some agricultural fields, which are also operated by the university for research. So they can sit a radar in a nice secure place inside the building and have it continuously monitoring what's going on in the agricultural fields. And then they're doing intensive measurements of what's actually happening in the fields. And then from these data, we're really trying to get sort of more insight into how best to use, if you got this more or less continuous radar imaging. You know, are there features of the temporal variation of soil moisture, of perhaps plant physiology that are beginning to show up in this? So there are some hints so far, but nothing definitive yet about, say, some new science of plant physiology that we might be able to observe. We've got similar experiments to be done over forests, and again, you know, continuous radar monitoring of these vegetation canopies to try to get us more understanding as to what science that there may be in that, and therefore how you could perhaps optimize the timing of your observations to get the best information. The next few slides are on the cryosphere. So this is just, again, a simulation of what we could do if we had a mission like Hydroterra. On the left, what Hydroterra could map of, say, so the snow amount as snow water equivalent. On the right, what we can currently do from point measurements over the Alps. And then in this case, it's looking at glacier response to things like weather events like rainfall. So that if you're able to measure fairly frequently, you can actually see a glacier in response to some local rainfall, you know, over a short period, starting to accelerate and then decelerate again as that sort of pulse of, I suppose it's lubricating water, having an effect on the glacier. And then sort of solid earth landslides, but also in the current version of the mission studies, we're actually looking quite a bit at what you could do in terms of tectonics, earthquakes as well. So this is all ground motion that using the radar interferometry, we'd be very sensitive to. And if there were sudden events like landslides, earthquakes, then with a mission like Geo, you could just point almost instantly to that area, start acquiring images. The societal impacts, well, with the water cycle, it's clearly got significant inputs for society. So part of the story we have to tell when we put our mission proposals together is that this isn't just sort of a little ivory tower exercise, but actually if ESA were to invest in this area of research, then we could actually have significant relevance to societal concerns rather than just answering a few science questions. And certainly with something like HydroTerra looking at water cycle and giving better insights into impacts like flooding, intense rainfall and so on, we think there's quite a strong case for this sort of high temporal frequency sampling. We've done some work really to try to sort of boil all these requirements together, looking at different sort of measurement requirements in terms of sort of temporal sampling, spatial resolutions and so on. I think the plot here is one that I really like, in that it just shows you how much more measurement capability a georadar potentially could give you. In that if you look at the boundaries, so the dashed line, this is the dashed line that represents anything to the above and to the right of those lines are what we could measure with HydroTerra. This is what we can measure with Sentinel in terms of the time scale and spatial scale. So Sentinel is good for spatial resolution, but relatively poor for temporal resolution. GPS is good for temporal resolution, but not so good for spatial resolution. So really, there just isn't anything that can really rival that combination of space and time that we can get from a mission like HydroTerra. And I think for many of these water cycle processes, those are very significant time and space scales that you can measure with a radar out in geo. So what are the prospects? Just got one slide, so I think this is pretty much my last slide here. Well, I really think that a radar out in geo would open a whole new window on our planet, and a radar there would really nicely complement what we can currently do with low Earth orbit systems, and also what we currently do have out in geo are infrared and visible band images. The meteorologists already know that geo vantage point is excellent for meteorology. It's fundamental to lots of the weather forecasts. So adding a radar there, that's a whole new layer of information potentially, which would have, I think, significant value to hydrometeorology. I suspect it would open up a whole new sort of set of measurements as well, and perhaps some new science areas in terms of those diurnal changes that you would see with radar. So this is the study that we did for ESA on Earth Explorer 10. So I hope that someone, like me or somebody else, will be able to come back in a couple of years' time and show you what the Earth Explorer 12 science study has revealed. And that's it, folks. Thank you very much.
Very much. Any questions? Can you do price that if you have two technologies?
Yes, yeah. So some of the other people in the team, I'm working with colleagues at particularly DLR in Germany and University of Politecnico di Milano in Italy. They're very excited about what you could do with more than one satellite, because it really does multiply up your imaging capabilities. You've got some quite nice possibilities there for doing some quite clever stuff.
I'm thinking specifically of things that won't have an isotropic radar scattering cross section, and then might look differently, might appear differently.
Yes, yeah, no, I think that's.
There's only uses for those, particularly like in agricultural monitoring.
I don't think that's certainly with radar. I'm not aware that that's been really done at the moment. But I think that's one of the things that I would like to see done. I'm quite interested in some of what you can achieve using passive techniques. Yes. So like using signals of opportunity. Currently, we've already got GNSS reflectometry, which is operational. I haven't seen it, but I just feel that there ought to be information there. If you've got GNSS, you have got these multiple imaging angles, because the GPS satellites are all over the place. So surely that tells you something about the canopy that you're looking at, or the soil surface or whatever.
Yeah. I've only seen that from Birmingham, where they had SDR radio receivers in campus measuring was scattered radiation from the GNSS satellite.
Yes.
But you suggest you get reflection from space.
It's done operationally from space. So Surrey satellites, SSTL, and the Surrey Space Centre demonstrated this, and they've got. I'm trying to remember the name. On Tech Demosat, they had a payload which did some. So that was launched, I think, about 2012, 2014. That collected something like 4 or 5 years worth of data of the GNSS reflectometry. I think it's the Cygnus mission, which is a US mission, which has actually got a constellation of small satellites carrying GNSS reflectors. And so that's sort of operational, I think, for tropical sea surface heights. Yeah. But, you know, that's an area I'd love to see more work done. I just think there's a lot of potential. And as you get this sort of modern capabilities for data processing, you know, surely there's a huge amount of electromagnetic energy bouncing around in our environment now. If we could only understand it and pick it up, I'm sure that would tell us a lot.
Some of the things that we've been interested in are anisotropy in the radar scattering process,
yes,
and multi-static radar. I suppose there's also multi-scattering. That's an interesting thing, you know.
Yeah.
So it's exciting. It's useful that we can get the data. So go to everything. By static polarimetry, see that pops.
Yeah, but part of what inspires me is, I don't know, people who are blind can learn to use their ears and sense the environment around them. I think if we could, you know, hear the electromagnetic environment around us, we could learn to interpret that to tell us all sorts of things about what's going on around us. And surely, you know, soil moisture, vegetation growth, you know, vehicles moving nearby, we'd be able to sort of sense all of that just by listening into the. Yeah, well, the baseline mission that we had was a single polarization. What we wanted to do was to have a transmitter circular polarization. If I talk about compact pol, does that basically you transmit circular and then receive on both, say, vertical and horizontal. And that's quite nice, I think, because you get reasonably strong signals in both of them. With this georadar, I've only been talking about the copolar backscatter. If you start to look about the cross-polar, you've lost another 10 decibels of signal, and that's making life very difficult for us. Whereas if you do the compact pole, where you're transmitting circular, you've only lost, I think, about 3 dB on each polarization. So that they're much more measurable, I think, much more useful signals to us. But the users aren't used to thinking about transmitting circular polarization and receiving these linear. So part of the motivation for those field experiments like hydrosoil is to try to get the users thinking about, well, would circular polarization work for them? Can they learn how to use that?
From Barley, I think
yes.
DB is more strong in spectrum than H8.
Yes, yeah. Yes, that's right. Yes, so yes. Yeah, certainly at C band, you know, if you've got a nice simple crop with vertical stalks, you would expect vertical polarization interact strongly with it. Sees the canopy, horizontal polarization sort of sees the soil in quite simplistic terms. That's how we think about it. But one of the challenges that we've got with these sort of missions is that we can come up with all sorts of ideas, but when you go to a funder like ESA, they say this is the budget cap. We really struggle as academics to know how far we can go in our ambition technically before we've gone over the budget cap. And so, you know, we're hoping to start a study in preparation for Earth Explorer 12 where we can work with Airbus in the UK to try to get some understanding of those trade-offs. How much ambition can we put in our technology and still stay within the budget caps? What I would really love for people who are smart on maths to help me out is, with these sort of systems, we've got so many signals going on similar space and time scales. You know, the atmosphere is changing, the orbit perturbations might be, you know, not quite as we think they are. The ground surface might be moving, you know, all sorts of things are happening. We need to tease apart all those different signals on different length and space scales. And also to know when we've got into a situation where we can't do it anymore, but you know, the weather's too vigorous, or that the land surface is too sort of unstable.
Sounds like a kind of uncertainty quantification and Bayesian, right?
Yes.
As usual, just recommendations.
Yeah, and you know, there is a lot of other information out there, isn't there? That, you know, numerical weather forecasts, databases about land cover, you know, about the weather statistics. You know, can't we throw all that information somewhere to help us unravel what's going on? I'll just check the chat, shall I? Just. Yeah, I don't see anything there in the chat, but yeah, for those of you online, we're looking at the chat. So if you do have any questions, please feel free to put them in there, and we'll try to answer them.
You know, that's us talking. Okay, I have one thing. Are you rushing off, or are you around?
No, I can be around for a cup of tea or something like that. Yes.
Thank you very much.
Thank you. So for those of you online, thank you very much for your attention.